Cool.
All right. Well, hey everyone. Thank you for joining. Welcome to the first episode of GPU mode of 2025. Thank you so much, Zihao, for joining. This is going to be our 41st lecture. So Zihao actually came as a recommendation from one of our former mods, like Byron, who basically described Zihao as one of the best engineers he knows. And as I was going over as I was going over the repo, the repos that you've created, I definitely started to really notice that. So I'm really psyched to have you here, and yeah, take it from here. I'll be monitoring questions on chat if anyone has any questions. So yeah, please get started.
Okay, cool. Yeah, thanks for the introduction, and thanks Baron for connecting me into GPU mode. And it's very exciting for me here to present our work on FlashInfer. So yeah, I'm a graduate student at UW, and currently I'm also part-time affiliated with NVIDIA. And FlashInfer is our work that have been done have been going over a year, and now it has been adopted in many inference engines. And today I'm gonna introduce a little bit about the attention part of it. So my talk title is about the efficient and customizable attention engine for ARM inference serving. And actually, FlashInfer is actually more than attention kernels, but today I'm gonna touch the attention part and see if it can inspire you and whether community has any inputs and help that can make us better. So yeah, to begin with, let me go into the why do we need another attention engine? So as all of you might have already known the VRM, right? So VRM was proposed to tackle the memory fragmentation of ARM inference serving because, okay, all of our ARM inference workloads have variable lengths. And if we preset a maximal sequence length for each of the sequence, then we will have a lot of memory fragmentation. So what VRM proposes is that, okay, we can have a data structure, they call it a page attention, that can organize all of the KV cache or pull requests as pages, and each at a granularity of something like 16 tokens as a block. And the page table is actually a concept in operating system so that we can just use the same techniques such as swapping and also something like a defragmentation to manage the KV cache efficiently. And in order to support efficient attention on page table, the VRM paper proposed the page attention that, okay, we do not need to, for each of the batch of requests, we firstly gather the data from the KV cache to a continuous KV cache, use the flash attention operator. Instead, they write a kernel that directly access the entries inside the page KV cache in order to achieve maximal performance in terms of memory efficiency. And this is a paper that maybe already 2 years ago, and VRM page table design is already the standard of the ARM inference serving engines. But actually, the original page table is only one of the options for KV cache management. Later on, there are some work such as SGLang. They propose that okay, we found there are a lot of opportunities of reusing the prefix in the KV cache, and they propose to, okay, we can organize the KV cache as a radix tree data structure. And it used a very special case of the page table that, okay, each of the page has a number of tokens 1. We call it a page size 1. And the benefit of this design is that, okay, we have a less fragmentation. And if we enable the prefix caching, we probably have a higher cache hit rate because we match a block if this token matches. Otherwise, we need to match the block if all of the 16 token matches. And all of the shared prefixes are organized as a radix tree. And SGLang also proposed many clever ideas, such as, okay, we can sometimes replace a subtree of the data structure. You can refer to their paper for details. And comparing the radix tree and the original page table design, you can find there are some difference. One of the significant difference is a page size of 1. Another difference is that, okay, here the radix tree explicitly modeling the shared prefix as a tree data structure. VRM can do similar thing by prefix caching, and we will feature that later. So now we have two kind of KV cache management design. And recently, another trend of accelerating the ARM inference is speculative decoding. For example, the Medusa and SpecInfer Sequoia. The core idea of them is like, okay, we have a draft model that generates a lot of candidates, and we can verify these candidates in parallel. In order to increase the efficiency of generating these candidates, and this paper is not only generating a chain of candidates, they generate a tree of candidates so that we can verify we can fed the entire tree into the large model to verify whether there is a path in the tree that matches with the draft model's output matches with the large model's output. And this poses some challenge in terms of the both the KV cache and the kernel attention kernel design, because if we look at the draft, if you look at the proposal generated by the draft model, it's actually we can organize this part of KV cache as a tree. So that is the third challenge that a little bit different from the previous work. And
so Zihao, do you mind if I interrupt with two questions? They're somewhat related, but like the first one is like I'm wondering like how you think about like broadly the design space of like KV cache management. Like do you sort of like still foresee this to be like a fairly active research area, or do you expect that something like radix attention is really one of the last things we'll need to build in this space?
I don't think it's the last thing. Firstly, for example, I think all of the KV cache design only focuses on the GPU only thing, right? And I know there are a lot of research projects that, okay, we are reusing the DRAM, we are also using as SSD, but I don't think there is a systematic work. I mean, there is a widely recognized modeling for this. So yeah, it's still active research area for me. Another interesting, I think, is that, okay, I think it has been explored in other areas before. For example, we can explore the similarity of some of the page blocks, right? So we don't need to exact match. We just, okay, the semantics of one page block is similar to the other one. We can probably merge them, but yeah, it might harm performance, but it is still a research area, in my opinion.
And so related to the question, considering it's still an active research area, how come like a lot of the sort of famous inference frameworks typically make a choice and don't seem to deviate from it? Like basically, like VLM, it's like, okay, we'll page attention, and then SU-line is like, yes, we're radix attention. Like why can't they just swap these things in and out?
Can you say it again?
So how come inference engine providers seem to be committed to a specific KV cache management technique as opposed to just exploring multiple at once?
I think each of the frameworks has their priority. I think one of the priority of SU-line is like, okay, we want to do structure generation where there are a lot of common prefix, and that is why they choose radix attention and radix data structure. Yeah.
Got it. Okay. Thank you.
Okay. Cool. Yeah. Thanks for the question. Those are pretty good. And I'm gonna later introduce how do we unify this KV cache design. Yeah. So another trend is, okay, we do not explicitly using the entire KV cache. There are a lot of techniques such as, okay, we can prune the KV cache, or compressing the KV cache, right? So one of the paper is called Quest, and it is from MIT and UW, and the core idea is like, we still organize all of the KV cache in page tables, but when computing the attention, we do 2 rounds of attention. In the first round, we compute we have something like the reduced keys for each of the block. And in the first round, we compute the importance of each of the page block by using the attention score between the query and the reduced keys. And after we compute the importance score, we apply a top K mask on it. So that's okay. In the second round, we only select the top K pages and compute the attention on these top K pages, the full attention on these top K pages. And in that sense, if we reduce k to a reasonable value, even if we are dealing with a pretty long context, for example, several million or even longer, and we can just set k to a relatively small value. And in the memory bandwidth, I mean, the I/O required for the second round of attention is more. And in the first round, because we are only computing attention on the reduced keys at the granularity of a page, so the first round k, the I/O for the first stage is also small. So in order to do this, we also require the specialized KV cache and also the attention kernel co-design.
You might be answering this later, but we have Dongyon who's asking,
Yeah.
Like considering you're talking about removing unnecessary computation, do popular LLM serving frameworks also leverage KV cache quantization?
Yeah, I think so. Yeah, int8 and FP8 are already standard setting for LLM inference engines. And I know that a lot of them also support the int4 or something like LLM deploy, which is a pretty good LLM serving framework. They have good kernels for int4 KV cache. But I don't have a very concrete idea about whether int4 can achieve ideal performance in terms of the reasoning task, something like that. But int8 and FP8, I think they're pretty decent, and a lot of, I mean, industrial and the API providers already provide such options. Okay, if there is no other question, I'm gonna moving forward. So yeah, here we introduce 4 kind of KV cache and attention computation challenges. And the way FlashInfer deal with them is like we use a unified data format called block sparse representation. And it is basically a generalization to the ordinary sparse matrix. And the only difference is like, okay, the minimal element of the sparse matrix is not a single scalar. It is a small matrix. We call it a BR by BC matrix. And the reason people prefer this format is like, it is more friendly to GPU tensor cores. For example, if you're looking at the NVIDIA GPUs, the minimal size of a MMA operation, it is something like a 16 by 8 by 16 for Ampere and even larger for Hopper. That means, okay, we need the minimal computation we can perform must align with the MMA shape of the GPUs so that we can use those hardware acceleration units efficiently. So if we do not pose constraints on the sparse data structure, we must do something like, okay, we look at how many of them we can block them together and form a MMA operation. But that is time consuming, and also in many of the cases we cannot form a block that is there are a lot of non-zero elements. So that is people prefer the block sparse format. And regarding the storage itself, we use the SciPy's BSR format, and where there are notations such as the index pointer, which records the start offset of each row in this entire packed value data structure. And the indices array recording the non-zero column index of each of the non-zero elements. And the value array, which is optional, indicates, okay, if we still need mask inside or value inside each of the BR by BC matrix, we need a value array. So fortunately, we found that, okay, the page attention can be modeling as a block sparse format. And for example, if we look at this example, there are three queries, 3 requests. Each request have different query lengths. And if we modeling the entire address space as a columns in the block sparse matrix, we can find that, okay, the pages being used by each of the requests is just, okay, the non-zero elements inside this block sparse matrix mask. And such finding is also in 10 years or maybe earlier, the graphics community has adopted similar findings that, okay, they're doing something reversely. They're actually modeling in graphics, there are a lot of hierarchical data structures that using sparse matrix. And what these people doing is like, okay, we are using page table, the TLB data structure, to help accelerating the lookup for the sparse data structure for acceleration. But here we're doing things reversely. Okay, we are trying to deal with a page table data structure, but we're modeling as a block sparse matrix. And as I mentioned before, that people prefer a block sparse matrix because the block size can fit the tensor cores perfectly. But if we just use the, so for example, 16 by 16 block, in some cases this might fail. For example, if you look at the tree speculative decoding, its attention mask is very sparse because it's basically modeling a tree-like structure as a sparse matrix, and the sparse ratio is very high. So if we use a minimal block of something like a 16 by 16, the outcome is, even though we can use tensor cores, but each of the blocks, there are more zeros than non-zero elements. And we still wasted most of the flows. And actually, most of the block sparse libraries, they are using a larger block size, such as 128 by 128. And you can imagine the wasted computation is actually more than expected. So the way we deal with this is like, we still use block sparse matrix, but we support a very flexible of the number of columns. And this is inspired by early work such as this paper called Efficient Tensor Core-based GPU kernels for structure sparsity under reduced precision around 6 years ago. And the core idea is like, we still use block sparse matrix, but the number of columns in the block is 1. And what is the benefit of this? You can imagine that previously, whenever there is a one non-zero element in a 16 by 16 block, we need to activate this block. But now the situation becomes, whenever there is one element in a 16, in something like a length 16 vector, we need to activate this vector. So previously we might wasted 255 over 256 elements, but now we only waste 15 by 16 elements. It is still wasted a lot of computation, but much better than before. So yeah, this is a very important design of the FlashInfer. We have to enjoy the benefit of using tensor cores while reducing the wasted computation introduced by the block structure. And actually, we found that, okay, the vector sparse data structure is friendly for the tensor core computation. The reason is that if we look at this example, say we want to compute the matrix multiplication between A and X, and what we can do is like, although the columns in A matrix are not contiguous in memory, and the rows in X matrix are not contiguous, but we can firstly gathering them from global memory to shared memory. After that, the data on shared memory is dense and can be fed into the KV cache, can be fed into the tensor cores. And one good thing about the ARM is that, okay, the last dimension is a head dimension in attention computation, and it is actually contiguous. So the gathering between HBM and to SRAM, we can actually, firstly, it's coalesced. We do not have the problem of non-coalesced memory access. The other issue is like, it is large enough because the head dimension is usually something like 128, and it can fit into the cache line of GPU architectures. So in this case, we can both have a high memory bandwidth by loading those sparse rows and sparse columns from global memory to shared memory, as well as using the tensor cores, using the dense tensor cores for the shared memory on-chip data. And
so sorry, Zihao, I'm wondering if you could talk a bit more about like the definitions for like an octet tiling and magic cube. Like this terminology is not too familiar to me.
Okay, so yeah, the reason I mentioned this is that they already adopted a similar strategy. Say, loading the sparse rows and sparse columns from non-contiguous global memory to dense shared memory, and applying tensor cores on the contiguous shared memory, something like that. Yeah. So I use these examples to show that okay, we don't really need the 16 by 16 block to use the tensor cores. We can actually using the vector sparse matrix to use tensor cores.
I see. So I guess here what you were trying to say is like these techniques are sort of useful outside of like basically this is part of like the HPC literature where they use like these kinds of techniques. I see.
Yeah.
Okay, got it.
We draw inspiration from these works. That is what I mean.
Oh, got it. Okay.
Yeah. Okay, cool. So in FlashInfer, we basically use the same technique to dealing with the vector sparse data structure. Another finding is that, for example, in SGLang's radix cache, we have a pretty large shared prefix, right? And it organized as a tree data structure. And we found that if we view this in terms of the block sparse matrix of this radix tree data structure, it's basically the shared prefix part can be modeling using another block sparse matrix with a larger block size. For example, if we do not pose any constraints, then the block rows should be a small value because there's no KV cache reuse. But now, if we look at the shared prefix part, you can see that for many of the requests, they have access to the same part of KV cache. So the block size, we can set a larger block size for this request. And actually, in terms of the block sparse matrix modeling, is basically decomposing a sparse matrix to several different sparse matrices, each with a different block size. And the benefit of that decomposition is that for the larger block size part, we can use the attention kernel by first loading the KV cache from global memory to shared memory and registers, so that we can use software to reuse those KV cache access. Otherwise, if we just using a smaller block size, we can only using the hardware managed, because the way kernel dispatches this computation is like for each of the block or each of the tile, we dispatch them to different CTAs or SMs in GPUs. So if we can have some prior knowledge of, okay, how many of them, we have a larger block size, we can just say, okay, this larger number of query requests, we can just, share access to the KV cache inside the kernel. So yeah, by such a composition, we can just enjoy the higher memory bandwidth because it can be, our kernel has already written such logic for the large block size. We using the shared memory to prefetch those KV cache. Otherwise, it will be going through the hardware managing. So yeah, if we, for example, in the case of there is a very long shared prefix and many shots unique suffix. In that case, using the software managed KV cache is much better than the hardware managed L1 or L2 cache. So yeah, this technique has also been proposed in many concurrent works such as hydrogen and trunk attention and something like that. And but the benefit of our modeling of using the block sparse matrix is like we can just using a unified way to manage the KV cache. Like for this shared prefix part, we can just using the composable format, say using different block sparse matrix for each of the parts of the entire KV cache, but without modifying the data. So we only record the indices and the data structures parts, but not its data. So it is very, very convenient for the KV cache management of the LLM serving engines. So yeah, that concludes our storage, the FlashInfer storage. We have the block sparse data structure and also the composable formats for prefix sharing. So for the next part, I'm going to introduce our computation-wise, our templates and our runtime and compilers. So to begin with, yeah, it is an old topic that have been touched by many of the work. It's the attention variance, because people nowadays are not using the standard multi-head attention proposed in 2017. People using the attention variance such as the group correlate attention and multi-head latent attention, and something like the logic subcap used in gamma and grok. So this attention variance only modify a little bit about the attention kernel, but usually requires modification. For example, if you are working on the flash attention code base, you need to change the kernel implementation. You need to change the glue code between C++ and Python, and that is time consuming. And you probably want upstream. You probably want merge them back to the upstream, and you probably cannot catch up with the latest library development. So yeah, there are some work such as the flex attention from PyTorch, which I really enjoyed and appreciated, that trying to deal with this problem. And our solution greatly draw inspiration from them. So we propose for our compute side, we propose a compiler and a runtime. For the compiler part, we draw inspiration from the flex attention work and let the user to customize their own attention variance by defining the functors, or you can just use them as functions. And our attention template supports continuous and the block sparse KV cache storage. And at the compile time, we have a compile time scheduling for different problem shapes. For example, depending on what is your hardware and what is your problem shape, whether you're doing prefitting, decoding, something like that. At compile time, we can do the dispatching to the best tile size, something like that. At runtime, we provide a variable length dynamic scheduling to adapt to different sequence lengths for load balancing, and the programming interface that is compatible with the open source LLM engines. So now let's go through the JIT compiler part. So our compiler part features a template written in CUDA and Katras, and for both flash attention 2 and 3. And we support the single request and batching, and most importantly, the block sparse data structures. With any block size, as I mentioned before, we can still use intensive cores with a small number of columns in the block. And we provide programmable functors for customizing the attention variance, which is inspired by flex attention. And to give you an impression, here is an example. Sigmoid attention is the attention variant proposed by Apple. And what they did to attention is that instead of using softmax, they are not using softmax, but applying something like a nonlinear function, the sigmoid function, to the attention logic. And this can be easily implemented by providing how do we transform the logic, to the logic. So we provide several programmable functors, the query transform, logic transform, and logic mask, which is similar to some of the score mode and mask mode provided by flex attention. And currently, we still need user to provide the attention specification in around, for example, 10 lines of CUDA code, and it can be embedded as a Python string. And we specify it into attention specification class, where we also provide the data types and the additional tensors and additional scalars passed to the kernel. And we will have a Jinja template that takes into the user provided attention kernel variant description, and also these data types and additional tensor scalars, and pass them to our Jinja template and compile them and register them as PyTorch custom operators.
So
yeah.
Zihao, I wanted to ask you a bit more about like that design choice, because like for example, like within like the PyTorch 2 stack with Torch Compile,
Yeah.
like they highly
Yeah.
leverage like these kinds of Jinja templates as well, and so does Flex
Yeah.
Attention, as far as
Yeah.
I know. But then other projects don't. Like for example, like I think like within JAX, like they'll use like more MLIR based like machinery,
Yeah.
and Cutlass they use C++ templates. And so I'm sort of curious, like, why you settled on Jinja templates as the right way to meta program for
Okay,
AP
so
users.
I have been working on machine learning compilers for a long time. So, but now I still using Jinja templates because I just think it's simple. Yeah, and easy for development. For example, if you use MLIR stuff, user need to recompile the project, something like that. But if you're just using Jinja templates, you just need to, okay, as Python side, we run something like a torch.load to loading this kernel. Yeah. But the drawback is that using Jinja template do not have anything like the type checking. And yeah, whenever there is errors, then it is very hard to debug. But in my opinion, it is mainly an issue for developers, but not users.
I see, but for users, they might prefer it because they can just like inspect the code that you ultimately generated for them, and that just makes things easier to understand. Okay, got it.
Yeah. Cool. Yeah. So yeah, it is very simple. We don't use any of the complicated compiler paths or compiler techniques for that. It's just string concatenation, but it happens to work. Yeah, that is fortunate. So yeah, we found that such abstraction can modeling a lot of attention variance. For example, the Libby attention, which also showcase using flex attention. I'm gonna not introduce that too much. But both Libby attention, sliding window, and custom mask can be described using our logic transform function, and we can also describe how to transform the queries to define something like the dequantization, or for example, pre-multiply the softmax scale optimization, like in that function, something like that. So actually, this attention specification declaration string is very powerful because we actually provide a structure that you can declare some of the members inside this structure. And we can just, for example, whenever activating this kernel, the kernel parameters will be specified in the parameter string, and we can do some calculations of we can compute something and store them in the members of this function. And that can be part of the register file inside the CUDA. So yeah, it can act as some optimization for some attention variance. Yeah. The next part of the attention template is about global to shared memory data copy, as I mentioned before, because the last dimension of the last dimension head dimension in query and key matrix here are actually contiguous. So yeah, we can still hit the GPU cache line size for maximal GPU bandwidth utilization. And on this figure on the left side, we show how do we load in data from sparse storage to shared memory. And then on the right side, we feature how do we load KV cache from dense storage to shared memory. After loading to shared memory, they are identical. They are both contiguous. But at global memory, they might be scattered or contiguous. So yeah, for the sparse storage, there is something like an index mapping, and we have to look up some of the indices array, which is stored in global memory in the block sparse data structures. And for sparse storage, we issue many of the LDG STS, which is the Ampere style asynchronous copy. For here is the typo. It's not one for each row, but one for each subwarp, something like that. And the reason we are actually using TMA can further accelerate data movement, but TMA 2D is unfortunately not applicable to the nonlinear memory access. For example, here the mapping between the global memory address and shared memory address is nonlinear. We need to go through a indirect indices array, unlike the contiguous tensor. So in this case, TMA 2D is not applicable. We fall back to LDG STS, but fortunately, we see that the performance is not influenced too much. And the main overhead is the registers, and we use much more registers than using TMA. And I'm gonna show that later in our evaluations. Yeah, we mentioned that we have a compile time tile size selection. The reason for that is that for ARM serving, we have a workload heterogeneity. For example, the traditional ARM serving can be decomposed into two phases. One phase for prefilling, which means when given the user input or given the context, we are doing the attention computation on the entire KV cache. The query size and the KV cache size is identical. And if you look at the attention mask, it's basically a triangle if we apply the causal mask. And after the prefilling stage, we are going to generate tokens one by one if we are not using speculative decoding. So if we look at the attention map, it is something like we're filling a new row in the triangle. And their computation are quite different because for the prefill case, the query length equals the KV length. But for decode case, the query length is always 1. And there is another case called, we call it a pen. And in some literatures, it's called incremental prefill. What I mean by that is like we are just extending maybe several tokens for example, when people doing speculative decoding, and the drop model might generate next 5 or next 10 tokens. And in that case, the query length is just 5 or 10. And another case is a multi-round conversation or something like techniques such as a trunk prefill, where we are filling maybe 1,000 tokens. That's not, the query length is a newly added 1,000 tokens, but it is not the entire KV cache. So in that case, the query length is less than KV length. And we are actually adding a trapezoid to this triangle of the attention mask. So their operational intensity of these stages are quite different. We need to select the tile size, carefully. So we provide a set of templates, and both in CUDA core implementation or tensor core implementation. For example, in pure decoding, if we are not using GQA, we are using multi-head attention, the operational intensity of the attention kernel is just 1. And we might prefer the CUDA core implementation, and we can have a very large tile size for it. But for the other case, in case of the appending or prefilling, or even decoding with a group query attention, because for group query attention, we can increase operational intensity because of the KV cache sharing for multiple heads. So in that case, we will just provide a set of attention kernels with different query tile size, 16, 32, 64, and 128. And given the input characteristics, for example, we know the average query length, we know some statistics of that. We can just select the best tile size for them, and we can pre-compile this collection of kernels. And for different architectures, we might tweak the pipeline design a little bit. For example, for FA3, and we have to adopt the WAP specialization for maximum performance. And our runtime scheduler is designed for, the compile time scheduler deal with the workload difference. For example, either it's decode or prefill. But runtime scheduler, what it does is like we look at the statistics of all of the requests inside a batch. So some of them might be long, some of them might be short. And what we're doing here is like we propose an algorithm that is dispatching. We first split the work split the attention of all queries into some of the tiles, and with the maximal size. The maximal size is the total number of blobs divided by the number of CTAs provided. And after we do the splitting, we're gonna do something like sorting all of the works from the maximal to minimal. And we are also maintain a priority queue of each of the CTA, and we are always putting the largest work to the CTA with the minimal accumulated work. And in that sense, after this algorithm is over, the number of work, the total cost of each of the CTA is nearly the same, nearly identical. And this part is currently executed on CPU, but later on we might dispatch it to GPU. And the goal of this algorithm is like, firstly, we want load balancing. If some of the sequence is too long, we must split it. And we also want zero wave quantization. So wave quantization means that some of the SMs and is not working, while some of the others there are too much work on them, something like that. So it's similar. We just want to make sure that all of the CDAs that we're executing are actually running and ends at a similar time. And our scheduler will be computing the map between the work and the CTA queue. And this map will be cached once we executing this scheduling algorithm. And we provide a attention kernel and the second stage of split K, the contraction kernel. We provide both of them in persistent kernel manner so that, okay, the kernel configuration is the same. So in the first stage of the attention computation, we will compute the output of each of the tile and store them in a temporal memory. We call it a partial output. And then in the second stage, we found that, okay, one request is being split into multiple work. We're going to merge them together. So in the second round, there's a contraction kernel that merges all of the partial output corresponding to the same request. Yeah. So actually, this algorithm is inspired by the stream K, but we are not directly using the stream K because we do not want to use atomic aggregation. Yeah, because per our discussion with many LLM inference serving frameworks, they want the kernel to have a deterministic output instead of some random output result from each of the run. So by default, if you use stream K, there's a reduction mode called atomic reduction, while the floating point aggregation order is non-deterministic, and that might result in some non-deterministic output. So here we guarantee our scheduler will have a deterministic execution order when never given the same input.
So yeah, as you were talking, like I couldn't help but think about the Sarati LLM and the chunked prefill work, which also deals with like load imbalances between prefill and decode.
Yeah.
And maybe two questions then. So like one is how does this differ? And two, like how do you sort of more generally think about the sort of scheduling space between these workload imbalances? Like what are basically the things that people should be considering?
Yeah, firstly, I agree that the serving frameworks can handle the load balancing thing. They do not necessarily need to batch the requests with different KV cache lengths together. They can just handle that at the serving framework's server side. But if you consider many properties, for example, recently there are a lot of concern about something like a fairness in terms of serving, right? And they just do not, they not only care about the performance, but they also care about, the reduction, the latencies variance across users. In that case, the serving framework might emit a batch where the sequence length might not be too similar. So I think it's still meaningful to handle the sequence length variance at the kernel side. But I think both would exist.
I see another question from chat, which is, how do you ensure that all SMs are active? Isn't CTA to SM mapping scheduler in CUDA undisclosed to the public?
So firstly, if you look at the H100 kernels, H100, they usually use one CTA per SM because the kernel itself already occupies most of the resources of both registers and shared memory, so that we cannot fit two CTAs into a SM. And for the other case, what we're doing is like CUDA provides the API to compute what is the maximum number of blocks that can fit into SM for maximum occupancy. So we first call that API to get a value. And we launch a kernel with a number of CDAs that maximum number of blocks per SM times the total number of XMs. So in that sense, I look at the kernel level provider, and it seems that all of them are just executing. Yeah.
Okay, that's it.
Okay, cool. Yeah, I'm gonna go ahead. So yeah, as we mentioned before, we also provide the programming interface that are compatible with the ARM serving frameworks. So the workflow is like we have 3 stages: the init stage, plan stage, and run stage. For the init stage, we are creating a data structure called wrapper, and we will take into the task information, for example, the problem size, and also if we are doing a JIT compilation of a new attention variant, you will need to specify the JIT arguments, and we will do the compilation there. And at the plan stage, the plan is executed at the beginning of each generation step. So the plan step basically do the several things. Firstly, is the load balancing algorithm I mentioned in the last slide here. And we guarantee the output is deterministic. And you might be worried about the cost of this plan stage, but actually what we can do is like, okay, because in most of the ARMs, we can reuse the same KV cache layout data structure across multiple layers. So we just need to plan once and reuse it for maybe 100 layers. So the cost can be amortized. And we also working together with some other ARM serving framework teams, so to do something like double buffering, to while executing the current steps generation, we are pre-computing the next steps plan, and that can further reduce this plan overhead. And the run stage basically executes the kernel according to the scheduling information generated by the plan function. And we make sure that our kernels themselves are compatible with touch compile and CUDA graph. And if we want to compute the ARM serving with CUDA graph, what we're doing is like, we firstly we need to warm up, and before we generate each step we call a plan, and we capture the computation of all layers in a CUDA graph. And during replay stage, what we're doing is like we first call a plan, and then replace the entire CUDA graph corresponding to the 100 layer computation. Not only attention operators, but also the layer norms thing and also the gem thing. Yeah. So here summarize our design. So we at storage side, we provide the unified block sparse data structure as our KV cache management unified data structure. And on the right side, we features our compiler and runtime. The compiler is actually a very simple string concatenation-based code generator that takes into a user-provided attention variant information and the task information. We are compiling the corresponding kernels, and we provide a ARM framework compatible wrapper data structures that can have the init plan and run stage, where the plan stage executes the runtime scheduler for sequence length information, and it will be executed per generation step. And at runtime, our kernel accepts the KV cache, which is the block sparse data structure, and also the queries. And our wrapper maintains a workspace buffer acting as the partial output generated by our split K algorithm. So here features some of our results. As we mentioned before, we are doing the block sparse. Internally we have a block sparse data structure, and we provide attention for both block sparse and contiguous KV cache. And here is the performance comparison. We select the page size of 1 on page attention for both the FA2 template and our FA3 template on the page attention workload pre-filling stage. You can see that for Flash Attention 2 templates, the gap between the contiguous KV cache and the sparse KV cache is more. So comparing the red bar and the blue bar, it is within 10%. And for the Flash Attention 3 template, the gap is a little bit larger, comparing the yellow bar and the green bar. But we can still achieve over 500 teraflops even for the vector sparse KV cache. And the gap is larger than FA2 template is that for FA3 template, ordinary people use TMA for KV cache memory for carry cache loading. But now we are falling back to Ampere style LDG STS for the sparse carry cache loading. And that caused some overhead of we are using more registers for the pointer arithmetics. If we use TMA, we can totally avoid the pointer arithmetics. So yeah, it is still the issue with, okay, TMA do not support of non-affine memory access. We hope it will be supporting later, but I don't know. Yeah. So because of the more register pressure, we must tweak the number of registers required for producer and consumer to make sure there's no register spill. Otherwise, the performance will degrade a lot. And after that, the tile size on KV dimension need to be reduced because we want to save some registers. So that is why FA3, the gap between sparse and dense is larger, but it's still tolerable in my sense. And regarding the variance, the load balancing algorithm, we are comparing the VRM's flash attention kernel library and the FlashInfer on several different settings. We generate a couple of settings where the KV cache length for each request have a constant distribution, which means all of the requests have the same KV cache size, and uniform distribution, which means the KV cache size varies between 512 to 2048. And another is a zip law distribution, which is a skew distribution. You can see that for the constant distribution, our performance are actually similar to the VRM flash attention because the algorithm we're using is basically similar. We are just using the FA2 template. But for the uniform distribution and skew distribution, we are better because of the load balancing algorithm. And on the top figure shows the decode stage bandwidth utilization. On the bottom figure, we are showing the prefill stage on both FA2 and FA3 template. And for both templates, we can achieve higher blocks utilization per prefill stage.
So do you have a question? Like one thing I've always been curious about, like when you're sort of saying something like we benchmark over real world variable length settings. Like I'm guessing concretely this means the zip distribution, right? Which is like 1 over, like basically my understanding of what zip is if you have a bunch of elements that are decreasing in order, then the nth element will be 1 over the index. And so like, is this really concretely what everyone uses to model real world lengths?
I would say this. Firstly, there's some study on the real world workload distribution, and it's not totally any of these distributions. So here is just a demo. Yeah.
I see.
Yeah. And but actually, according to many of the company have such statistics, but yeah, they might not willing to make it public. So here I tend to say we are just making a simulation.
Got it.
Yeah. So yeah, here's the end-to-end benchmark. We are using the SLN, and we comparing with SLN also provides a Triton backend, and we are comparing on both the Llama 3.1 8 billion and 70 billion model on one H100 instance and 4 H100 instance. And we can see that we can achieve up to 2 times latency reduction compared to the Triton backend. And because we have the main issue is that we can support we have the benefit of using the latest NVIDIA features such as warp spatialization, which Triton might support very soon. But here, using the Cutlass and CUDA template still has some benefits. And another thing is like we have a specialized memory loading modular design that for gathering the sparse rows from global memory to shared memory, which is currently missing at Triton. But later on, we believe Triton is good, and we are willing to support a Triton backend. So yeah, here we show the case of some of the customized attentions that fuse, for example, in streaming RM, they use the fuse rope attention because they cannot pre-apply the rope and store the post rope carry cache on the post rope key and values to the KV cache according to their design. So we must have a fuse rope attention kernel. And yes, by using our customization, we can just achieve 2 times acceleration at kernel level compared to not fusing them. And also at the end-to-end level can achieve 30 times end-to-end intertoken latency reduction. And we also mentioned that for shell prefix, we use a composable data structure. Say using the larger block size for the shell prefix part and smaller block size for the Unix suffix part. And here is some example on parallel generation, which is measured on shell GPT. And shell GPT, OpenAI API provide a parameter called n, which means, okay, we're going to parallel generate n different responses in parallel. And in that case, those responses, we can treat them as different requests, but with a shell prefix. So in that case, we are measuring the performance of the using composable format over using a single format in different n settings. You can see that for the moderate size, for example, between 4 to 32, we can achieve decent speed up of around 50% for intertoken latency, and also the at maximum, we can achieve 20% speed up in terms of the time to first token. And when the n grows larger, actually, unfortunately, we do not observe any more acceleration. This is mainly because of the serving works themselves. They have some other overhead. In that case, especially for the parallel generation, in that case, attention is not a dominance factor. But for this is a result generated by the MLC engine, and we're still porting it to SGLang and VRM. So yeah, in general, we still think it's promising to get a good performance for the structure generation and the parallel generation. So yeah, so here is our community is originally this project at first is a research project. And after 1.5 years of development, we have more than 15 contributors from both industry and academia, and we have been adopted by open source ARM engines, for example, the VRM, SGLang, and MLC engine, TGI, and something like that. And we are still growing, and we welcome currently our roadmap and our features that we want in the future are public in our GitHub issues, and we are welcome to contribute whatever you want or leave comments. And our position is to expanding on existing kernel libraries such as PyTorch, kubeBLAS, and similar libraries. And because we believe that if we want to achieve the best performance for ARM inference serving, we cannot totally rely on libraries because they are statically compiled and designed for certain shapes. But for ARM inference serving, we need to firstly co-design with algorithms and also co-design with the different. We need flexibility. So yeah, we focus on both attentions and gem, and also ARM specific operators such as sampling, which is another important feature of FlashInfer, but I don't have time to feature today. You're welcome to use that. And our mission to make good open source CUDA kernel generator and library for foundation models. And we have a Slack channel. You're welcome to join the community and for discussion and back reporting, something like that. So in the next few minutes, I'm gonna touch a little bit about our next steps. One of the next steps is kernel support for nanoflow style parallelism. Nanoflow is a research work from UW that's trying to achieve optimal ARM service throughput. And the core idea is like we are going to split the request into nano batches. The nano batch is just more fine-grained split of batches. Say, for example, previously we are executing the GMV and the QKV production, something like that. But now we are splitting the data into batches, and the GMV production can be split to GMV 1.1, GMV 1.2, something like that. And we found that the attention operator, some of them are IO bound, some of them are compute bound. So by fine-grained splitting, we can just, doing pipeline parallelism inside this batch of data between the nano batches and overlap the compute bound operators and IO bound operators. The green operators are IO bound and the yellow operators are compute bound. And the blue operators are just communication operators, and they can all be overlapping together. The way NanoFlow achieves this is using they call it an intra-device parallelism, which means we are executing the compute bound operators, memory bound operators, and network operators at different SMs within the GPU. For example, in H100, there are 132 SMs in the GPU. You can allocate in 100 of them for gem and 30 of them for maybe attention and 2 of them for networking, whatever. And this requires to executing those kernels with a limited budget of SMs, not total SMs, and using the GPU's multi-stream feature to do that. So currently we are trying to add in the support of the kernels that's executing with a limited budget of SMs, which can be specified as a parameter when executing this kernel. And we're starting to doing that for attention, which is actually the NanoFlow work is using FlashInfer, but it didn't get upstream, and it modifies the FlashInfer code base, but yeah, in a fork. So they already done this, but we're going to bring them back to FlashInfer mainstream. And also, in order to, we can not only do this for attention, we also need to do this for gem and communication operators. So we also need to support the executing gem on a subset of SMs. And some of our community members is working on that. And CUDA actually provides a feature called green context, which allow us to executing some operators with a subset of SMs. And I looked into the PyTorch. I didn't see there's a green context support in PyTorch, but I believe, yeah, using green context will be also a good feature for both PyTorch and ARM serving engines. And we are looking for its support in the future. Another next step item is fully reproducible ARM serving kernels. And the reason is that, yeah, as reported by the community, our kernel output among different batch choice might vary. For example, if one request is executing standalone, it has one output. But if it is batched together with other requests, for example, in a batch of 128 requests, the output of the total ARM generation output might be a little bit different from if you're only executing one request. That is because if there is only one request, we tend to use split K and stream K to split the KV cache into chunks to maximize the SM utilization. And in that sense, the floating point accumulation order is different from just executing the request of all batches. And because for some of them, we do not split. For some of them, we split into 4 chunks and 8 chunks. The accumulation order is different, resulting in a huge difference, especially after 100 layers, something like that. And that can still give you reasonable output, but for some of the use cases, users require full reproducibility, considering a case that some people using ARM for data compression. They first using the ARM to compress the data as a rank of the output corresponding to the largest, and then use this rank array for decompression. And I read a small demo, but we found that, okay, if it's a kernel choice for the compression stage and decompression stage, if there's a little bit discrepancy, the overall compression and decompression algorithm is totally doesn't work, because we cannot tolerate any of the difference in terms of the ranking. Otherwise, the total output is not meaningful. So what we need is that we want a full reproducibility between prefill stage and decode stage, and probably different machines, but I do not expect the same behavior between CPU and GPUs. But at least for same kind of GPUs, we need to have the full reproducibility. And we also want the reproducibility for different batching choices. The kernel output for a single request and 100 requests should be the same. So in that sense, if we want full reproducibility, we might sacrifice some of the performance because we disable but it's critical for some of the workloads such as the and we created a RFC for comments, and if you have any interest, you can contribute later. We might add a flag to the supports reproducible stack. And there's also some exciting working items from the community. For example, Chi is working on the flex attention alignment, and our goal is to provide a CUDA backend for flex attention stage now. And he created a repo called FlashInfer Jam, which is the initial stage of our alignment with flex attention. There are still other things that are not supported yet, but we are going to push this forward in the next couple of months. And another exciting item is from Sue Bing, DeepSeek MARA acceleration, MARA decode at now in the main branch, and we're going to support later on support the tensor core based MARA decoding kernel and the the H100 version of ARM decode later in the next month, and please stay tuned. So yeah, that is all of my comments today, and feel free to ask any questions. And yeah, I really welcome your input and feedbacks.
Thank you, Zihao. You took us on a tour de force of like so many different angles of LLM inference, so thank you. So yeah, so like Zihao said, if you have any questions, like please post them in chat. I'll just be reading them out with your username. In the meantime, I did see one question from Coffee Vampire.
Yeah.
So he's basically wondering what is basically what range of attention patterns are modelable using flex attention? So for example, what he has in mind is a function like differential attention, which takes the difference of two softmaxes. And he's sort of wondering if there are any attention patterns that you cannot model with flex attention.
Of course. For example, the linear attention, I think the computation pattern is totally different, right? Because for linear attention, people tend to first multiply K and V and then multiply it with Q, right? So in my opinion, the space that flex attention like framework it covers is something like first multiply Q and K, and we have an element-wise operator that is customizable, and also followed by something like a customizable scan operators. Here, the scan means, for example, online submax is a kind of scan, right? So yeah, the flash attention is basically we use the online submax here, but we can customize it to something else. So I think whatever we can cover is just like, okay, we have a custom element-wise operator applied to Q and K and V, and customizable scan operator on the intermediate stage, and maybe at the end we have a epilogue, something like that, and that is the space we cover.
All right. Well, thank you so much. Yeah, I don't see any questions in chat, so thanks again for joining. Cool. So for everyone on the call, the slide and the lecture should be available very shortly. Tomorrow, we also have another lecture. We're going to have Adam Peshke, who's going to be here talking about Mosaic GPU. So if you like this lecture, I think you'll like tomorrow as well. Thank you so much, everyone, and thank you, Joe.
Cool. Thank you. Have a good day.